This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on Arcsine and Arccos functions in general. The other video was just first quadrant analysis. This will be general analysis. So we take a look at our sine function. Sine of 0 is 0. Sine of pi over 6 is a half. Sine of pi over 4 is 1 over root 2. Sine of pi over 3 is root 3 over 2. Sine of pi over 2 is 1. These need to be committed to memory, but you can certainly develop them from 30, 60, 90 triangles, 45, 45, 90 triangle, and the unit circle. Similarly for cosine, cosine of 0 is 1. Cosine of pi over 6 is root 3 over 2. Cosine of pi over 4 is 1 over root 2. Cosine of pi over 3 is a half. And cosine of pi over 2 is 0. So we take a look at inverse functions. We have to remember that a function has to pass the horizontal line test. When we create an inverse, x becomes y and y becomes x. For that to work, the original must pass a horizontal line test. So if you're looking at a function, it will only have an inverse if it passes a horizontal line test. That is, a horizontal line cuts it in at most one point. But if we look at y equals sine x, you'll notice a horizontal line cuts it in an infinite number of points. So we're going to need to restrict the domain of sine x to define the range of the arcsine, or inverse sine of x. So here is our sine function, and the question is, where is it one-to-one? Where does it pass the horizontal line test? Certainly not here. From 0 to pi, a horizontal line cuts it in two places. But maybe from negative pi over 2 to pi over 2. Notice in that range, no horizontal line would hit in more than one place. And that's exactly what we use. We restrict the sine function from negative pi over 2 to pi over 2. So that when x becomes y and y becomes x, this restricted domain becomes the restricted range for arcsine of x. So this is how we usually write the arcsine function, sine to the negative 1 power. So the range of the arcsine function will be from negative pi over 2 to pi over 2. Whenever we have an arcsine, the answer has to be between negative pi over 2 and pi over 2. Or the fourth quadrant, but really the negative first quadrant to the first quadrant. So let's take a look at the arcsine of 1/2. We want that to be theta. So what do? We ask ourselves, we say, the sine of what angle is a half? And we know one of the answers is pi over 6, but there's an infinite number of answers. Pi over 6 is in the first quadrant. In the second quadrant, 5 pi over 6 is an answer. We could also add 2 pi to pi over 6 to get 13 pi over 6. I could add 2 pi to 5 pi over 6 to get 17 pi over 6. I could subtract 2 pi from pi over 6. That would give me negative 11 pi over 6. So there's an infinite number of answers. This is where that range comes in handy, because we said the range had to be between negative pi over 2 and pi over 2. Pi over 6 is not in that range. 13 pi over 6 is not in that range. None of the other values I gave you were in that range. So the only one that is pi over 6. And that will be the arcsine of 1/2. There can only be one answer. If it's a function, we can only have one answer, and the arcsine of 1/2 will be defined as pi over 6, as the one value between negative pi over 2 and pi over 2. Let's look at our next example, the inverse sine of negative root 3 over 2. So I need some angle theta where negative root 3 over 2 is the sine of theta. Well, let's think of reference angles first. The sine of what is positive root 3 over 2? And that's 60 degrees, or pi over 3. But where is sine negative? Sine is negative in quadrant 3 and quadrant 4. So we could have two answers there, but we want to find one between negative pi over 2 and pi over 2. So thinking all of this through, indeed, the sine of pi over 3 is root 3 over 2. Where is it negative? In quadrant 3 and quadrant 4. Well, in quadrant 4, I certainly could have gone all the way to 5 pi over 3, but knowing what I know about the range of arcsine, instead I said, let's think of that as negative pi over 3. So negative pi over 3, rotating pi over 3 in the negative direction, the sine of that is negative root 3 over 2. That's the quadrant 4 answer. The quadrant 3 answer would be 5 pi over 3. I don't think that's right. Let me fix that. Fix it. In quadrant 3, it's pi plus the reference angle pi over 3. Pi plus pi over 3 is 4 pi over 3. So the sine of 4 pi over 3 is negative root 3 over 2. And the other quadrant 4 angle would also be 5 pi over 3. That's pi over 3 short of 2 pi. That would also work. But I'm required to choose one in the range. So I have to select a value between negative pi over 2 and pi over 2. So this quadrant 4, or thought of better as the -1 quadrant, this will give me my answer. What we're looking for here is negative pi over 3. So the arcsine of -√3/2 is negative pi over 3. I need a fourth quadrant answer, thought of as a negative value. Negative pi over 3 is my result. Again, a function to have an inverse, it has to pass the horizontal line test. Here's cosine. Same deal. Any horizontal line will intersect an infinite number of points. You need to restrict the range so it only hits one point at most. So again, here's another version of our y equals cosine x. So where can I define this? Now, not negative pi over 2 to pi over 2, which I did for sine, because again, a horizontal line there would hit twice. But how about from 0 to pi? That would give us first and second quadrant. Cosine in the first quadrant is positive and the second quadrant is negative. Indeed, this is the piece I want. I'm going to restrict the domain here to 0 to pi. Now it is 1 to 1. Now it passes the horizontal line test. So currently x is between 0 and pi. When I take an inverse, x becomes y, y becomes x. So my range of the inverse cosine will be from 0 to pi. That's what we're looking for. So our first example on the inverse cosine is the inverse cosine of 1 over √2 is theta. So I need some angle theta that equals 1 over √2. But there are an infinite number of them. Pi over 4 is the most obvious one. Negative pi over 4 in quadrant number 4 would work, as would 7 pi over 4, another name for that. We could add 2 pi to pi over 4 to get 9 pi over 4. There are an infinite number of answers to this question. But the range for the inverse cosine is from 0 to pi, so I picked the one here between 0 and pi. And which one is between 0 and pi? The answer, of course, is pi over 4. Our next example is the inverse cosine of -1/2. We want that to be theta. So -1/2 is the cosine of theta. So the reference angle, cosine of pi over 3, is 1/2. Which quadrants is cosine negative? I guess quadrant 2 and quadrant 3. So reference angle is pi over 3 in quadrant 2 and in quadrant 3. Well, in quadrant 2, it's pi minus pi over 3, which is 2 pi over 3. Quadrant 3, it's pi plus pi over 3, which is 4 pi over 3. So I have 2 pi over 3 could be a possible theta. 4 pi over 3 could be a possible theta. Of course, I could add 2 pi to this, which would make it, what, 8 pi over 3. But I need to find an answer that is in my range. And for the inverse cosine, the range is from 0 to pi. So is 2 pi over 3 between 0 and pi? I think it is. 4 pi over 3? No. So I want the second quadrant answer. My answer theta here will be 2 pi over 3. So the inverse cosine of -1/2 is equal to 2 pi over 3. How about the inverse sine of the sine of negative pi over 4? Well, negative pi over 4 is in quadrant 4. Hopefully we can visualize that. So the sine has to be negative. Sine is negative in quadrant 4. Reference angle is pi over 4. That's the angle between the x-axis and negative pi over 4. So the reference angle is pi over 4. So the sine of negative pi over 4 is negative because it's in quadrant number 4. Sine of the reference angle, sine of pi over 4, so this is just -1 over √2. So now I have the inverse sine of -1 over √2. Or sine of theta equals -1 over √2. Sine is negative in quadrant 3 and quadrant 4. Reference angle is pi over 4. So what do we get in quadrant 3 and quadrant 4? I want to choose a value between negative pi over 2 and pi over 2. So I think I'm going to want the quadrant 4 answer. So sine of theta is -1 over √2. Well, let's think about this. Reference angle is pi over 4. To put it in quadrant 4, how about negative pi over 4? And indeed, that's the answer. So in this case, you can see inverse sine and sine sort of cancel as you would expect inverse functions to work. However, that doesn't always happen with inverse sine and inverse cos, with arcsine, Arccos. For example, if I have the inverse sine of the sine of 7 pi over 6, 7 pi over 6 is in quadrant 3. In quadrant 3, sine is negative. The reference angle would be pi over 6. So the sine of 7 pi over 6 is negative, since it's in quadrant 3, of the sine of the reference angle, the sine of pi over 6. Negative sine of pi over 6. So the sine of 7 pi over 6 is -1/2. So this becomes the inverse sine of -1/2, which means -1/2 is sine theta. So what is the theta that I need? Well, sine is negative in quadrant 3 and quadrant 4. The quadrant 3 answer is not going to work for me, but the quadrant 4 one can, because I know that I've got to choose the angle between negative pi over 2 and pi over 2. So if I take pi over 6 in quadrant 4 and make it negative, that would be negative pi over 6. So my answer here is theta is negative pi over 6, which notice, inverse sine of 7 pi over 6 was not 7 pi over 6, it was negative pi over 6. So it's important to go through the entire process when we're doing this analysis. Our next example is the inverse cos of the cos of 3 pi over 2. Well, thinking of the unit circle, 3 pi over 2, 270 degrees. The x value is 0. The cos of 3 pi over 2 is 0. So now I have the inverse cosine of 0 is theta, so 0 is cos theta. So when does theta give a cosine of 0? Well, pi over 2 and 3 pi over 2. Those are two cases, and then add 2 pi to all of those. So adding 2 pi to pi over 2, we get 5 pi over 2. Certainly negative pi over 2 would also work. That's in the fourth quadrant. But I have to choose a value between what? Between 0 and pi. That is my range of the inverse cosine function. So which one of these is between 0 and pi? Only the pi over 2. So that's our answer for the inverse cosine of the cos of 3 pi over 2. How about the sine of the inverse cosine of 2/3? I'm going to let theta be the inverse cosine of 2/3. Cos of theta is 2/3. Let's draw a triangle. Cos is adjacent over hypotenuse. Adjacent over hypotenuse, 2 over 3. Cos of theta is 2/3. Now can I solve for b using Pythagoras? 2 squared plus b squared is 3 squared. 4 plus b squared is 9. B squared is 5, so b is the square root of 5. You'll notice our original question here is the sine of inverse cos of 2/3. That's the sine of theta. Looking at this, what is the sine of theta? Opposite over hypotenuse, b over 3, root 5 over 3, which I'll quickly show here. So there we go. Sine of the Arccos of 2/3 is the sine of theta. Sine theta is opposite over hypotenuse. Opposite is root 5, hypotenuse is 3. So the sine of the inverse cos of 2/3 is the sine of theta, which is root 5 over 3. One last question on this lesson. The cos of the inverse sine of u. I'm going to let theta equal the inverse sine of u, which means sine theta is u. But let's make that sine theta u over 1. And we know sine is opposite over hypotenuse. So let's draw a triangle again. The opposite is u. The hypotenuse is 1. We'll fix that. Fixing that, the sine of theta is opposite over hypotenuse. The sine of theta is u over 1. Let's call this other side a. What do we know? U squared plus a squared is 1 squared, thanks to Pythagoras. So a squared is 1 minus u squared. A is the square root of 1 minus u squared. So making that a square root of 1 minus u squared, I want the cosine of the inverse sine of u, which according to this is just the cosine of theta. But what do we know about cosine? Cosine is adjacent over hypotenuse. So the cosine of theta will be, this thing will be this a, root 1 minus u squared divided by 1. So indeed, adjacent over hypotenuse is just root 1 minus u squared. That will be the cos of the inverse sine of u, and that will conclude this lesson.